Okay, so picking up where we left off yesterday, we left off with J.J. Thompson's cathode ray experiment, and we learned that this cathode ray, basically was yanking negatively charged particles away from atoms, creating this beam of particles that were negatively charged. They bent or deflected toward positive charges, and we're able to measure that the ratio, the mass to charge ratio, was something of the order of 2,000 times smaller than hydrogen, which led him to believe that he discovered a piece of the atom, later called the electron. And of course, the plum pudding model is the model where we have this diffuse amount of positive charge surrounded by the particles. Okay, uh, right up until about 1910, 1911, it's around there exactly, 1910-ish, if I can say that. Ernest Rutherford, called the father of atomic theory. J.J. Thompson was called the grandfather, but again, he was the first to discover a particle of electron. Ernest Rutherford, okay, had a very famous and probably the most important of all the experiments, the gold foil experiment. And let me explain what happened here. Ernest Rutherford dealt with radiation. He actually first discovered two of the earlier forms of radiation, alpha and beta radiation. Okay, alpha, Greek for A, and beta for B, so thus A and B. Any case, what he had was he noticed that some metals gave off alpha particles, and we're going to learn later in the course that radiation is the work of metals that have unstable nuclei. They change their nucleus by doing something. And an alpha particle is a helium nucleus. And I'm going to tell you it's made of two protons. So I'll put those little P's in here. And two neutrons. We haven't defined them yet. You've heard about them. So two neutrons, two protons are what an alpha particle is. And this comes right from a nucleus. So when I say an alpha particle, it's basically two protons, two neutrons coming from a nucleus of an atom. In any case, some metals give off alpha particles to make their nuclei stable, and we'll talk more about that. So we've got these alpha particles that are shooting out of this container, metal with a small opening to direct the charge. And this experiment was actually born out of some very eager undergraduate and graduate students who just wanted to do something around Ernest Rutherford. He was a god to a lot of people, and he became even bigger, if that's possible, after this experiment. So he actually gave this experiment to do. He was busy trying to study different forms of radiation, and at the same time they were studying the components of an atom. It was happening at the same time. In any case, he gave them a very thin gold foil, or a very thin metal to shoot from. And he asked the students to sit in a room for about an hour to adjust their eyes. And basically what he had was a scintillator. A scintillator is an object, when hit, lights up. And before he put the very thin metal foil is just a very thin metal, he had the students sit, okay, Ernest Marston's Hans Geiger, sit and watch, okay, where these particles hit, and had them count the flashes. When a alpha particle, two neutrons, two protons, would hit the container, the container would flash, and they would count. So let's pretend, I don't know the actual data, but in 1 hour time, okay, after they sat in this dark room for an hour to adjust their eyes, let's say they counted 1,000 flashes. So for every hour, 1,000 alpha particles come out of this box, and that was a constant rate. Radioactive decay doesn't change over time, it's constant. So this would always be a constant number. So they came up with that. Okay, then they put, okay, this gold foil in its way. And lo and behold, when they recounted very thin, they got, let's say, 970, okay, hits. Okay, and so they lost 30. When they went up to tell Ernest Rutherford, okay, about this, they said, well, you probably did it wrong, so do it over and over again. They did, and they kept missing about the same number. So he suggested that they just move around to see where the others might be. So they spent hours, painstaking amount of hours, okay, and they just changed their position. So if they were looking right here, then they would look right here for an hour. Then they would look for here for an hour. And over time, by looking at the different positions, basically sitting in the dark with a magnifying glass, they found all 30. And what they found was, where were these particles? They found some beautiful deflections, some pretty amazing deflections, and even, this is most incredible, they found some deflections that almost came directly back to the, I did this poorly, sorry. These deflections, I should have circled the entire thing. These deflections almost bounced directly back, but those are far and few in between. So they really encapsulated, they encapsulated almost this entire object. I don't know what's going on here, but they basically encircled this metal sphere, and they were able to, again, spend painstaking amount of hours and look at every position, and they found all of the 30. Took hours because you can't just watch the entire screen. And what they found was some deflected, okay, and some actually bounced almost straight back. Okay, now of course the ones that bounced straight back were like 3 out of the 30 that missing. Most of the others were just deflections, and very few, went this far. Most of them, okay, went right through. Like 970 went right through without any changes in direction. Of the 30, some were major deflections, and some were even real major deflections that almost bounced straight back. So there were far and few between the ones that bounced straight back. Now, when they ran and told Ernest Rutherford about these results, supposedly the story goes that he dropped a piece of equipment that now was worth $1 million in his hands. His jaw dropped. And what he interpreted was that from this, he was able to discover something very important. If you look at the atoms, okay, remember, the gold foil is a few atoms thick. I'm just going to draw one. They expected everything to go through, okay? Because remember, the model of the atom was positives and negatives. Okay, the negatives were that plum pudding that were just haphazardly put in the atom, and the rest of the space, the interstitial space, was this, glue of positives. So the positives were spread out over. So if you got something that has 2 protons, very positive. Now, they didn't know about protons. They just knew that the particle was very positive, and 2 neutrons. It's a pretty big particle. It should rip through this very diffuse, spread out matrix of positives. So we'd expect all of them to go through. Okay? But what really happened was, if I redraw the atom, or a very thin piece of atom, some of these deflected. Most of them still went right through, as we would suspect, but what we didn't suspect is these big deflections. And what we didn't suspect is the ones that almost bounced straight back. And the reason is because the entire mass of the atom was in the nucleus. And the only reason why these guys would deflect like they are is because the nucleus, where all the mass of the atom is, must have been positive. So we have a positive nucleus. So Rutherford discovered the nucleus of an atom. You say, what's so important about that? Well, it's important because you start arranging these things in a certain position. All of the mass of the atom was in the nucleus. And that mass included protons. Now, he didn't know about protons. He discovered protons a few years back, and neutrons were actually found about 30 or 20 years later or so. But neutrons and protons make up the entire mass of the atom. And electrons that J.J. Thompson discovered earlier, okay, were outside this framework and are in this empty space. Now, they don't take up mass of the atom because, remember, they're 2,000 times lighter than these guys, protons and neutrons. So for the first time, we're putting together a model of the atom where we have this nucleus, this very dense, thick nucleus. It's positively charged, and most of the atom must be just empty space where electrons are in. So let's go back to our drawing. So the Rutherford model, okay, is nothing more than having a nucleus filled with protons. That was discovered a couple of years back. And then, of course, 20 years later, we have the neutrons with electrons that are on the outside somewhere in that empty space. Okay, so this is now changing, okay, from this idea of a plum pudding to now a dense core called a nucleus. So what did he discover? He discovered the nucleus of an atom. He's actually to measure it. Now, how did he measure the actual distance? For probability. How many hits bounced off and the deflections and the angles. He was actually able to figure out the probability of deflections and angles to get an actual distance, which was, I believe, 1 times 10 to the negative 1 times 10 to the negative 10 meters. Any case, he discovered a nucleus, but more specifically, he discovered that most of the atom is empty space where the electrons roam. Okay, and of course, he discovered that the nucleus is a dense, positively charged, and he knew it was positively charged because he was positive about it. No, because the deflections of this positive particle, he called an alpha particle, deflected away. We now know it's positive because of the 2 protons that make it positive. Okay, so it deflected away when it got close, like my drawing shows right here. So when a particle comes close, it would deflect away. If it got too close, it would bounce back. Now, those deflections were far and few between. Why? Because this is so small. The rest of the particles went right through. Okay, so he discovered that the atom is mostly empty space. The nucleus is positive, and the entire mass of the atom is a dense core where all the mass is located. So mass of atom is in this dense core. Okay, so important parts. Atom is empty space. The nucleus is a dense piece of matter. All the mass is located, and it's positive. Okay, now from his experiments, Rutherford had some people that worked under him that discovered the neutron. Okay, that's Henry Chadwick, and he did it with some nuclear equations that I'm not going to show you today. And then we have someone go Moseley, and he didn't discover protons, but he discovered that different atoms had different number of protons. Rutherford discovered protons through nuclear equations as well, but Moseley through X-rays saw a ratio of basically reflected X-rays back in whole number ratios based on the proton number. So these guys, this is about the 30s, and this is also around the same time. So we basically were able to now know that protons and neutrons in the nucleus, electrons in the outside.